Hey there, another screencast. This is on the topic we're not talking about in class, but it could be useful, it could be interesting to you, so I wanted to put it out there. This is also described in our text, but I thought I could do it quickly with a screencast, so let's give it a try. The topic is method of shells. It's an alternative method for creating an integral that gives you a volume of a solid. So the method of shells gives you an alternative method for exhausting the volume of a solid of revolution with shapes whose volumes are easy to calculate. If you think about how we've calculated volumes so far, take a solid of rotation. You rotate a curve around the x-axis, you get a solid. And then we take that solid and we take a cross-section of it. So in this case, we get a cross-section this way. It's a circle. And we'll measure an area, figure out what the area of that circle is as a function of where we took the cross-section. And then the volume is the integral of that cross-sectional area, where the limits of integration are the limits of where we can take that cross-section. This next method is called the method of shells. The quote-unquote cross-sections we take are different. I don't know what to call the shapes. I don't know where the word shells comes from necessarily, but I'm going to write this. The shape we use in the method of shells, I'm going to put this in quotes, are tubes. And you'll see what I mean. So we're going to have these kind of like cylinders with a hole in them, like washers. We've talked about washers. Okay. And they're going to have an axis in the middle. So there's going to be an axis. And from that axis, they're going to have an external radius, a big radius, and then they'll have a small radius, we'll call that little r, and they've got a height. And the volume of this kind of shape, it's very easy to calculate because it's the volume of the disk with the larger radius, in this case it's pi r squared h, minus the volume of the disk that you remove to get that inner radius, pi r squared h. And you can do a little bit of algebra here. And you can do a little bit more, and we're going to do this. When we do this, and you'll see, this is going to be interesting to us because it's going to play the role of delta x. Anyhow, this is the shapes we're going to use. These pictures are a little bit challenging to draw, so bear with me. Let's start the method of shells. To start this going, we're going to let ourselves have a function that's continuous. On an interval AB. And for the purposes of my derivation, I'm going to make sure that A is strictly positive, and I want the function to be a positive function. I want A to be positive because we're going to rotate around the y-axis, and I want F to be positive because we're going to look at the region between the function and the x-axis. So consider the solid created by rotating the region between the x-axis and y equals f of x on the interval a to b about the y-axis. So the region, of course, might look something like this. And that's the region that we'd be interested in rotating about the y-axis. So you'll see in a minute when I do the cut 'em up and add 'em up step that we always do when we create a definite integral formula. I'm going to have a partition points here, and when I swing this region around the y-axis, they're going to swing around too, and we're going to pay attention to the lines that they trace. Okay, so let's do it. So we have a function on a to b. I'm going to say that's the function y equals f of x. And we're going to swing it around the y-axis. And so I'm going to sketch the mirror, if I can, around the y-axis. And then I'm going to sketch in the contours of the shape that we get when we revolve it. So there's an edge here of our region, there's an edge here of our region, and those swing out that way. So this gives you a sense of what the solid looks like in 3 dimensions. It's got a bowl at the top, and then there's a hole in the middle that you can pass through, because there's, in our region, there's nothing there. So the step 1 in our process of creating a definite integral formula is always to subdivide something, in this case it's our interval from a to b, into n subintervals of equal width or equal length, and that length we're going to denote by delta x. And the second step is we're going to call the endpoints of these intervals xi. And as usual, xi is going to be x naught plus I times delta x. Follows that same pattern. So I'm going to draw in here an xi minus 1 and an xi. And each of these, when we swing the region around the y-axis, what I want you to watch is these vertical lines that connect the point on the x-axis to the associated point on the graph of the function. What they do is they trace out curves on the solid. Let me trace out curves down here on the bottom too, of course. And what you get here is like a sheath or a layer, or and then for each of these subintervals you get another layer. Right? So our solid is subdivided into these layers. Now each of these layers is, because our function is curvy, each of these layers has a curve in it, so we don't have a good formula from geometry to calculate the volume of this layer. So what we're going to do is that we're going to approximate each layer with a shape that we can calculate its volume for, and that's going to be the tube I showed you before. So I'm going to take the height here, so I'm going to take this rectangle, and as you sweep this rectangle around the y-axis, it sweeps out a tube. And the volume of this tube isn't quite the same as the volume of the slice, but it's close. There's a little bit of error in the volume approximation, but that's okay. As delta x gets narrower and narrower, that difference will get smaller and smaller, and it'll effectively go away. So let me write down the details for this step. So in step 3, the xi trace out what I call the layers of the solid. Okay. And the ith layer has a volume that we'll denote by V sub I. So if V is the volume of the solid, then V is the sum of the volumes of the layers. Each layer is approximated by a tube, and I'll draw the tube over here so we can label its dimensions. Okay. And it has external radius x sub I. It has internal radius x sub I minus 1. And it has height, according to my picture, of f of x I minus 1. It doesn't matter which endpoint you choose. I'm choosing the I minus 1 partition point for that. So just to be clear, over here in our picture, what I just drew here would have been the x-axis. And so our partitions points would be here, this would be xi minus 1, and this would be xi. And that would be how they trace out the tube. And the height of our function here would be the height at the internal point of the tube. Okay. With this, the volume of our ith slice is approximately equal to pi radius squared times the height minus pi radius squared times the height. Right. This is the volume of the approximating tube. It approximates the volume of the layer. So the total volume is approximately equal to the sum of these. So I'm going to write this. I'm going to pull pi out. I'm going to pull f of xi minus 1 out. And then I'm going to leave xi squared minus xi minus 1 squared. Right? So here's our approximating formula for the volume. Now we're about ready to apply the calculus, the limit. Copying this over to save some work. Taking the limit, as n goes to infinity, this becomes v equals, right? The limit turns the approximation into equality. The limit of the sum as I goes from 1 to n of pi f of xi minus 1 times xi squared minus xi minus 1. Oh, yeah. But we need to do a little work here first. Okay? There's two things that are wrong. Where's the delta x? And the other thing is both xi and xi minus 1? You gotta be kidding. So this is where we write the difference of those two squares. You can factor it, and the other factor, so here's one factor, the other factor is xi minus 1, and that's just delta x. So now this definitely looks like a definite integral. But we're not quite there, because I got both of these things here. But as n goes to infinity, delta x goes to 0, so xi gets closer and closer to xi minus 1. So this right here is getting closer and closer to 2xi minus 1. So we can say this limit is the same as 2 pi xi minus 1 f of xi minus 1 delta x. And this is exactly the definition of the integral from a to b of 2 pi x f of x dx. And that's the formula for the volume of a solid using the method of shells. There's a lot going on in this picture, so it takes a little bit of thought and reflection to understand when the method of shells are useful. But there are times when the method of shells is the right method to use. Sometimes you get a choice. You could use the method of shells or the method of disks or washers. But sometimes there's no question that this is the method to use. I'll make a screencast with another example or two in the next few days. But for now, here's the method of shells. Enjoy it. Cool tool. It's not one of our learning targets, but I thought you'd enjoy seeing this. See you later.